This is a quick comparison of like how ice versus Henderson-Hasselbalch will work out for a simple weak acid calculation. I've got a straightforward setup here, get a pH and then get a pH after we add some strong base to our weak acid solution. And I picked acetic acid, CHQ-H as we might call it, because I happen to know the Ka value. The Ka value is 1.8 times 10 to the minus 5. All right. So you'll see me use acetic acid and hydrofluoric acid and ammonia as real common examples because that happens to be Ka values that I remember. All right, how to approach problems in general, and I guess that's important in how we're starting out here. We got to get a pH. We've got some weak acid. We're going to have to write an equilibrium system. In this case, we got CH3. And I would have written this out in advance, but I think it's important enough to see the process that goes into these every single time. So every single time, write that aqueous dissociation equation. Every single time, write that Ka expression. In this case, it's H3O plus and CHQ over CH3 COOH. And we happen to know that value for Ka is 1.8 times 10 to the minus fifth. All right, so there's our basic setup. And again, like when you're setting up an equilibrium problem, I would just start out with ice. If I don't know anything else to do, I would fill in the information I have right off the bat. In this particular case, we've got 0.10 molar, and so that is our initial amount. H2O we're not worried about. It's the solvent. H3O plus is 10 to the minus 7th from autoionization. And CHQ, the acetate polyatomic ion, is 0 because we haven't made any yet. We're going to lose some amount. If our K value was large, we'd lose all of it. But it's not large, and so we're only going to lose some of it. And I don't know how much that sum of it is, so we have to do some math here to figure that out. The amount we lose there will be the amount we gain there and there. 0.10 minus x, x, and x. All right? In this particular case, then, we get a situation where we have x times x over 0.10 minus x. These equilibrium amounts are the ones that I'm looking at for that calculation. And this is supposed to equal 1.8 times 10 to the minus fifth. Punching that into the calculator, I get a x value of 1.3 times 10 to the minus third. And I can use that to get a pH. Since that x is our concentration of H3O plus, my pH is going to be the negative log of that x value. And in this case, that happens to be 2.88. All right? And that's our answer to part 1, I wrote. Should have called it part A. All right, that's our answer to part 1. Now, part 2 says we have to do something else. We have to add 0.025 moles of NaOH. And I didn't really cheat, but a common idea in these problems is that we're going to keep a constant volume. And I intentionally chose a latent constant volume of 1 liter because that allows me to use moles and molarity interchangeably for this. All right? So this is the part where a lot of people get stuck. And I think that looking ahead at what we need to do, one of the strategies I tell my students is look at what you have and then figure out what it can do. Well, I've got acetic acid and I've got NaOH. My aqueous dissociation equation has acetic acid in it. It doesn't have NaOH in it, so I'm going to need some other equation to make that work. And my space budgeting is not super great right here. So I'm just going to do that up here as stoichiometry. All right, and I guess I'll start that out in green. So what do I have? I have this and this. What can they do? Well, let's take a look. All right, that's an acid-base equation that I think most people would recognize. We're going to end up with sodium acetate and water, right? We're not worried about a K value or anything. This is a strong acid, strong base situation, and it's all going to react and cancel out. So let's see what happens. I'm going to do stoich here, and actually that's something I want to mention. Spend a ton of time learning how to set stoich up with halves and needs and everything else, and all of a sudden I throw it all out the window so that I can do things a lot faster here. All right, so this is not going to be ice, but it's going to be in the place where we would do ice. This is going to be stoichiometry. Stoichiometry, not ice. And so in this particular case, I've got 0.10 molar of that. And our NaOH, I have 0.025. Now that's moles, but it's in 1 liter, so that's a molarity as well. It doesn't matter. I could have called this 0.01 moles or whatever. I haven't made any of this yet, and I'm not worried about that. So this is stoichiometry. I have 2 reactants, 1-to-1 stoichiometry. This is going to be my limiting reactant and my excess reactant, so I'll subtract that 0.025. I'll subtract that 0.025 because that's how much we're going to use up, and then I'll gain 0.025. That leaves me with 0.075 and 0 and 0.025. Now the important thing here is I now have a buffer. I've got some weak acid along with its conjugate base. All right, so a mixture of a weak acid and its conjugate base gives you a buffer solution. Something I didn't mention, and again, I think this is something that someone may ask, which is like, oh, what about the sodiums? Well, they're just there as spectators to balance charge. So that's how we end up. All right, now I have 2 amounts, and I can go over here and do ice. And I'm going to tell you in advance, you don't actually have to do ice. That's the whole point of this problem. But let's do ice first just to see how it compares. And I don't want to rewrite that entire system. So this was for number 1, and now we're working on number 2 right there. Again, the difference is our initial conditions are these things over here, that 0.075 molar. I don't have H2O, 10 to the minus 7th for the H2O, sorry, H3O plus, and then 0.025 molar right there. So it's the same setup as this, it's just that we have this common ion effect. And in the big picture, this is how buffers work, which is now when I add acid or base, I've already got stuff on both sides, and that creates a resistance to moving in either direction, and that's how buffers work. All right? So let's see how this change takes place. It's a weak acid. Once again, I'm going to have minus x, and I'm going to have plus x and plus x. But since there's already some of this here, it's going to be harder to go in that direction. 0.075 minus x, and then we have x and 0.025 plus x. All right, and these are my equilibrium conditions that I'm going to plug into that Ka expression. So we end up with x times 0.025 plus x over 0.075 minus x. And in this particular case, when you solve it, you find out that x equals 5.4 times 10 to the minus 5 molar, which results in, when you take the negative log of that number, a pH of 4.27. All right? And that is our answer to that second question. So the question is, did we really need to do ice there? And the answer is no, we can shortcut it with the Henderson-Hasselbalch equation. Anyway, let's make this a clearer 1 and this a clearer 2 right there. All right? And then now we'll deal with like 2 alternate, we'll call it, or something. Right? We're going to use the Henderson-Hasselbalch equation. So Henderson-Hasselbalch. In that setup, as we showed in a previous video, the Henderson-Hasselbalch equation just says that pH for a buffer system is pKa plus the log of whatever amount of A minus we have over HA. Okay, our conjugate base over our acid, and we just said that this is our weak acid and its conjugate base, which makes it a pretty quick calculation. We need a pKa. I know my Ka is 1.8 times 10 to the minus 5th, so pKa, pKa, it's going to be the negative log of Ka, which is going to be the negative log of 1.8 times 10 to the minus 5th, which gives us 4.74. So if we want the pH of our solution, it's going to be 4.74 plus the log of our A minus and our HA. All right, our A minus is the 0.025 and the HA is the 0.075. And if you're not sure where those are coming from, they are coming from our stoichiometry earlier, right there and there. All right, when we plug that in, you get a pH of about 4.26, which is slightly different than that 4.27. Henderson-Hasselbalch does give us an approximation, and the closer to pH being pKa, the closer that approximation is. But in this particular case, to be able to use this equation instead of doing all this work is quite a time saver. All right, so I'm going to declare these are the same, put a smiley face, and either of these we could label as our answer to number 2. So once again in slow-mo, when you just have a weak acid or weak base situation, you're going to have to do ice. If you then add some conjugate to that weak acid or weak base, you now have a buffer system, and you can still do ice after you do your stoichiometry, or you can just do stoichiometry and plug it right into the Henderson-Hasselbalch equation. So in another video, we'll look at the much more complicated version of that.